Right now, Earth is flying into a cloud of gas 30 light-years wide. Out at the edge of the solar system, a bubble bigger than every planet combined soaks up about 70% of the radiation deep space throws at us. And that bubble is shrinking. So if it gives out while we cross into this new region, what reaches the ground? And would you survive it? Hold on to that question. The answer is the very last thing you'll hear. We are drifting out of the cloud that has shielded us for 100,000 years into a patch of the galaxy almost nobody has mapped. And by the end, a layer of radioactive dust on the ocean floor is going to tell you whether you'd survive it. Stay with me. Start at the bottom of the Pacific. Drill into the crust, and in layers laid down between 1.5 and 3 million years ago, you find something that should not be there. Iron-60. It's a radioactive form of iron that does not form on Earth. It is forged in the heart of exploding stars. Its half-life is just 2.6 million years, short enough that every atom we find had to arrive recently from outside. The conclusion is hard to escape. One, maybe two stars detonated within about 300 light-years of us, and the debris rained down through the atmosphere and settled into the sea. This already happened. A nearby star blew apart, and Earth was dusted with its remains. And here's the part that should make you sit up. Traces of that same Iron-60 are still falling today. And it isn't only the ocean floor. When astronauts carried home rock from the moon, the same radioactive iron was hiding inside it, in lunar soil that has no sea and no weather to wash anything in. Two different worlds, sharing nothing but the same patch of sky, both stamped with the fingerprint of the same explosions. When a signal turns up in two places that have nothing else in common, you stop calling it a coincidence. Remember this dust. It's the proof the shield has limits, and to see those limits, you have to go to the edge of it. In 2012, a spacecraft the size of a car did something nothing human-made had ever done. Voyager 1 reached the edge of the bubble and flew into a wall. Not a solid wall, a wall of superheated hydrogen piled up where the sun's wind slams into interstellar gas, glowing between 30,000 and 50,000 degrees, close to 89,000 degrees Fahrenheit. This is the boundary of the heliosphere, the sun's protective shell, and it sits about 121 times farther out than Earth's orbit. Voyager took 35 years to crawl there. The moment it crossed, the readings flipped. The sun's particles fell away, and the count of cosmic rays from deep space jumped. For the first time, we measured the shield from the outside. And what we learned is that this wall is not a fortress. It moves. It breathes. And what makes it breathe is exactly where we're heading. Here's something that bubble doesn't want you to feel safe about. Even at full strength, it only stops about 70% of the cosmic rays heading our way. 3 out of every 10 already get through. So let's be clear about the two shields you have. The big one is the sun's bubble, far out at the edge of the solar system. The small one is Earth's own magnetic field, right over your head. This whole story is about the big one being pushed in, and the small one was never enough on its own. Step partway out of it, and the leak turns real. Fly from New York to Tokyo over the pole, and you absorb a dose of radiation you can actually measure. In parts of Europe, airline crews are legally classified as radiation workers for exactly this reason. That's the leak at 70% protection. Go higher, and it stops being abstract entirely. Astronauts on the International Space Station, still tucked partly inside Earth's magnetic field, soak up in a single day what you'd get from the natural background down here over months. Strip that field away, the way the whole planet would if the bubble were driven inward, and there is nothing left standing between living tissue and the open fire of the galaxy. So ask the obvious question: what happens if that 70% drops? Remember this number, 70%, because in the final minute, it's going to decide whether you'd survive. But first, you need to know where Earth actually is right now. For most of human history, we assumed the space near the Sun was empty. It isn't. The solar system is currently flying through a specific clump of gas astronomers call the local interstellar cloud, or less formally, the local Fluff. It's about 30 light-years across. It glows at around 7,000 degrees, almost as hot as the surface of the Sun, and we drifted into it somewhere between 44,000 and 150,000 years ago. Our ancestors were painting cave walls when Earth entered this cloud. The only reason it doesn't cook us is that it's almost unimaginably thin, fewer than 1 atom in every 3 cubic centimeters. And that thinness is doing us a favor, because the density of the gas outside the bubble decides how big the bubble can be. Thin gas, big shield. Thicker gas, and the shield gets pushed in. And we even know the cloud is moving. Not still. A NASA spacecraft called IBEX sits near Earth and literally tastes the interstellar helium drifting through the solar system. Atoms from the cloud itself streaming past us at around 25 kilometers a second. That's how we know we aren't floating in a quiet pond. We're standing in a wind, and the wind is made of another region's air. So what happens when we leave this thin cloud? That's where the story turns. This is the heart of it. We are not staying in the local Fluff. We are on our way out. Astronomers estimate the Sun will leave this cloud somewhere in the next 10,000 to 20,000 years. And some analyses suggest we may already be standing in the doorway, in a transition zone where our cloud presses against the next one, called the G cloud. Here's why that's the reason for this entire video. We genuinely do not know what density we're moving into. If the next region is denser, the interstellar gas pushes harder against the Sun's wind, and the protective bubble shrinks. The wall that sits at 121 times Earth's distance could be driven inward. In the most extreme scenarios scientists have modeled, the heliosphere could shrink so far that the planets, Earth included, are left outside it, exposed to the raw interstellar medium. To feel the scale, look at the probe that found the wall. Voyager 1 is now more than 24 billion kilometers away, and it took almost half a century to crawl out there. That distance is the current reach of the shield in one direction. Now picture that boundary driven inward, past Pluto, past the planets, until the entire buffer that took a spacecraft 47 years to cross simply closes in around us. If that just rearranged something in your head, you already know what the like button is for, because now we have to talk about what exposed actually means for you. So picture it. Not a movie apocalypse, a normal Tuesday. You wake up, the lights work, the coffee machine runs. Nothing looks different. But the air above you is now carrying a heavier rain of high-energy particles, and everyone is a tiny bullet. Most pass straight through you, harmless. A few strike a strand of DNA in a single cell and snap it. Multiply that by every cell, every day, for thousands of years, and you raise the background rate of mutation and cancer across every living thing. Electronics feel it too. Cosmic rays already flip bits in computer memory and have glitched aircraft systems. More radiation means more of that. And higher up, the same particles chew at the ozone layer that blocks the sun's ultraviolet. The danger was never a fireball. It's a slow, invisible turning up of a dial nobody can see. Your phone already lives with a hint of this. The tiny errors cosmic rays cause in electronics have a name: single event upsets. and engineers deliberately design memory chips to survive the occasional hit. Now imagine that hit rate climbing, quietly, year after year, across every satellite, every power grid, and every aircraft at once. Which raises a question you can answer personally. And here's a real one. How exposed is where you live? The higher your latitude and the higher your altitude, the more of this you already get. A city like Oslo or Anchorage takes more cosmic radiation than one sitting on the equator. So tell me in the comments where you're watching from and how high up you are. I want to see how many of you are living in the places that would feel this first. Now zoom out, way out. The local Fluff and the G-cloud are tiny clumps inside something enormous. Our whole neighborhood sits in a vast, nearly empty cavity called the local bubble, roughly 300 to 400 light-years across. And it didn't form gently. It was blown open by somewhere between 14 and 20 supernovae that detonated over the last 10 million years, sweeping the gas outward and leaving the hollow we now drift through. So the calm, thin space that keeps our shield large isn't permanent peace. It's the aftermath of an explosion, the inside of a blast wave that hasn't finished moving. The clouds we're crossing are the leftover wreckage, drifting back in. The stars that did it even have an address. The leading suspects belong to the Scorpius-Centaurus Association, the nearest nursery of giant, short-lived stars, the kind that burn fast and die as supernovae. Over millions of years, a string of them detonated like a slow burst of fireworks, each blast carving the cavity wider. We didn't drift into empty space by luck. We're sitting inside the scar, and that reframes the radioactive iron from the start of this video. It wasn't a freak accident, it was a sample. Now I have to be honest with you, because this is where it's easy to lie. We cannot say a supernova caused any specific event in Earth's history. What we can say is measured, not guessed. The iron 60 in the seabed is a measurement. The timing, repeated pulses around 2 to 3 million years ago, is a measurement. And some researchers have proposed, carefully, that the extra radiation from that era may line up with a cooling climate and even shifts in how life evolved. Proposed, not proven. That's the honest line. But here's why it still matters. It means the thing we're describing is not science fiction. It has a fingerprint in the rock. The shield has been pushed before, the radiation has reached the ground before, and we are made of organisms that lived through it. And in 2025, researchers pushed it one step closer to home. They proposed that the surge of radiation from those nearby blasts, around 2.5 million years ago, may have driven a spike of mutations, including in viruses circulating in Africa, right around the window when our own ancestors were taking shape. Proposed, again, not proven. But it drags this whole story out of deep space and into our own bloodline. So the only real unknown is the one we started with. What comes next? And here's the last thing almost no one realizes before we close the loop. We don't have to imagine the bubble shrinking. We watch it happen on a small scale every decade. Every 11 years, the sun's activity drops, its wind weakens, and the shield contracts. The cosmic rays measured here at Earth climb by double digits, right on schedule. We have already seen the dial move. The interstellar cloud just decides how far it can swing. Which means everything now comes down to the question I asked you at the very beginning. So, if the shield thins while Earth drifts into the wrong patch of space, what reaches the ground, and would you survive it? Here is the answer the whole video was built around, and it is not the one the title promised. The region of space we're entering can strip away the shield. That part is real. But the twist is this: it already did, and you are the proof that someone survived. That radioactive iron at the bottom of the ocean, the dust I told you to remember, is not a warning about the future. It's a receipt from the last time. A star exploded, the bubble was pushed in, the radiation reached the sea, and life kept going. You're descended, unbroken, from everything that lived through it. And that number I asked you to hold, the 70%? When the cloud last pushed the shield inward, the 30% that leaks became more. Not enough to end the story, just enough to bend it. You are the proof the math came out survivable. The shield was never a wall that keeps the universe out. It's a tide. It goes out, it comes back in, and right now we just happen to be living at high water. The only thing we don't know is which kind of cloud is on the other side of the door, and whether the tide pulls back a little further next time. And the unsettling part isn't the danger, it's the clock. This doorway takes thousands of years to cross. No one alive will see the far side of it. We are standing in the gap, reading the radiation in the rock behind us, and guessing at the room ahead. A room we will never live long enough to enter. Which leaves one strange thought to carry with you. Every shield you trust, the planets, the suns, your own skin, isn't a wall. It's a tide, and the only real question is whether anyone's still measuring it when the water goes out. If you want to keep watching the universe try, and fail, to be quiet, subscribe, and I'll see you in the next one.